Hello. In the last class, we were talking about the thermal conductivity. We know the thermal conductivity coefficient kappa is equal to 1 by 3 CVL. Here C is the heat capacity per unit volume of the crystal, V is the velocity of phonon, and L is the mean free path of the phonon. The mean free path of the phonon gas is determined by two processes. One is scattering of phonon with the crystal boundary and imperfection, that is imperfection. The scattering of phonon from the imperfection or the crystal boundary may cause a change in mean free path of phonon gas. Similarly, the phonon may collide with another phonon, or the interaction scattering by other phonons. Okay. So two kinds of scattering may occur for a phonon. Phonon interact with another phonon. So the scattering from other phonon cause a change in mean free path of the entire phonon gas, or scattering of this phonon from the wall of the crystal, or any imperfection in the crystal. There will be a scattering. There may be a scattering with this imperfection. Okay, that also cause mean free path to change. So here, if we are considering the atoms in the crystal are interacting harmonically. If there are only pure harmonic, if the atoms interact only harmonically. If the atoms interact only harmonically, there will not be any interaction between phonons. So phonon may interact only with the walls of the crystal and lattice imperfection. Therefore, the mean free path is limited by only this geometrical scattering. Okay, that means the scattering by walls of the crystal and the lattice imperfection. The second type of scattering is absent because there will not be any interaction between phonons in the harmonic interaction. But if lattice interaction is anharmonic, then there will be coupling between phonons. That means phonon interact with other phonons. So that causes the mean free path to change. That means it limits the mean free path. Let us see how the mean free path change in the anharmonic interaction case. Okay. The frequency of collision of a phonon with other phonons is directly proportional to the number of phonons with which the given phonon can interact, which is directly proportional to the temperature T at high temperature. Okay, so the frequency of a phonon with other phonons is proportional to the number of phonons with which the given phonon can interact. Okay, and this is proportional to temperature T, because at high temperature the number of excited phonons is proportional to temperature T. Number of excited phonons is proportional to temperature T at a high temperature. Okay, so you get this 1 by raised to h nu by kT minus 1 is proportional to kT by h nu, that means h cross omega. So here when at high temperature h nu by kT, that means h cross omega by kT is this h cross omega by kT is very small. So e raised to x minus 1 will become 1 plus x minus 1 is this is 1 plus 1 plus x minus 1 is 1 by x. X is h cross omega by kt. 1 by x is kt by h cross omega. So this is the thing. So at high temperature, the number of excited phonons is directly proportional to temperature T, which is the frequency, which is directly proportional to the frequency of collision of a phonon with the other phonons. And frequency, therefore, frequency is frequency of collision of a phonon with the other phonons directly proportional to temperature T. Okay. So when frequency is directly proportional to T, mean time for a collision tau is directly proportional to 1 by T. Okay. You know the mean free path is V into tau, and for a within the medium phonon velocity is constant, therefore the it is directly proportional to the mean free path is, therefore the mean free path is directly proportional to 1 by T at a high temperature. So at a high temperature the mean free path is directly proportional to the temperature, inversely proportional to the temperature of the specimen. Now, when we talk about the thermal conductivity in a crystal, the one end of the crystal, we are considering one end of the crystal in thermal equilibrium at a temperature T1, and the other end of the crystal is in thermal equilibrium at a temperature T2. Okay, so that means there should be a mechanism in the crystal by which the distribution of phonon is brought into local thermal equilibrium. So therefore, there should be a way of establishing a local thermal equilibrium distribution of phonons. The collision of phonons with the crystal boundary and imperfection will not establish thermal equilibrium of phonons because there is no change in energy of individual phonons during these collisions. Okay. So, and also a collision of a three photon collision. So, geometrical collision or geometrical scattering of phonons will not establish thermal equilibrium. And also three phonon collision of the type of the form two phonons are interacting with the wave vector k1 and k2, then the total when they interact k1 plus k2 is equal to wave vector k3. If this is the relation of the wave vector, then this also will not establish a thermal equilibrium because there is no change in the momentum of the phonon system. So the total momentum of the phonon gas is conserved during this collision, this type of collisions. This also will not cause thermal equilibrium. Okay. So to establish a thermal equilibrium, there should be three phonon collision of the form K1 plus K2 is equal to K3 plus G. So these processes establish thermal equilibrium of phonons. Okay. So in this first case, this is first expression, this second expression. In the first expression, there is no change in the total energy, total momentum of the phonons. So there will not be any thermal equilibrium, because during thermal equilibrium, to establish thermal equilibrium, some phonon has to lose energy, some phonon has to gain energy, and so the total there should be transfer of energy. So that will not happen when the change in momentum is zero. When K1 plus K2 is equal to K3 plus G, there is a change in momentum of phonon. So in this case, so this type of collisions causes a thermal equilibrium of phonons. Okay. So the second type of process is called Umklapp process. Umklapp process. So this process is called Umklapp process, whereas the first kind is called normal process. Okay, so the collision of the form K1 plus K2 is equal to K3 plus G, where G is the reciprocal lattice vector. Reciprocal lattice vector. So in this case, there is a net change in momentum. In normal process, there is no net change in momentum of phonon gas. Okay. So normal process or N process, this is called N process. This is also called, the second type is also called Umklapp process or U process. So the difference between Umklapp process and normal process is that Umklapp process establish thermal equilibrium of phonons, and a normal process will not establish a thermal equilibrium. Okay. At high temperature, most of the interactions are Umklapp process. Let us explain it in the using in the K space. We can differentiate the N process and U process using this diagram. So this is K1 vector, this is K2 vector. So if we add these two, then the resultant is, this is the resultant. In the K space, we plot the wave vectors K1, K2 are the wave vectors of the individual phonons 1 and 2, and the resulting wave vector of the wave vector is K3, that is the K3 is the wave vector of the scattered phonon. Then these kinds of a process is called N process or normal process. Okay. When K1 and K2 are sufficiently high, then the K3 will go out of the first Brillouin zone. The resulting wave vector will go out of first Brillouin zone. We know that the physically significant value of a wave vector of a phonon is a wave vector which is inside the first Brillouin zone. So for any value outside the first Brillouin zone, there is a corresponding, there is a equivalent wave vector inside the Brillouin zone. Okay. So in Umklapp process, we can draw the plot of this wave vectors. So in this case, the resultant will be So in the second figure, it shows the Ohm-Clap process. Here, K1 plus K2 gives a wave vector which is outside the first Brillouin zone. So an addition of a wave vector G, which is the reciprocal lattice vector, we can bring back this wave vector into the first Brillouin zone. So okay. So this is the resultant wave vector. So K3, this is K3 vector and this is G. So K3 plus G. So here in the normal process K1 plus K2 is equal to K3. Okay, no problem with this K3 because it is already inside the line zone. But here, since the resultant is going outside the first Brillouin zone, so we have to get the real value, I mean the significant value of the wave vector inside, that is K3. So here K1 plus K2 is not equal to K3 but is equal to K3 plus another vector G. Okay. So from this point and this point, this point and this point are equivalent. Okay, because the point outside this Brillouin zone is there is a corresponding point inside the Brillouin zone. So to that point we can draw a vector that is K3. So K1 plus K2 is equal to K3 plus G. Okay. This G is a reciprocal lattice vector. This kind of process is called Ohm-Clap process. Ohm-Clap means in German it's a fold over. Okay. So we are just taking it back to the first Brillouin zone. So this process is called Ohm-Clap process. So Ohm-Clap processes are responsible for establishing thermal equilibrium of phonons. Now let us see how the geometrical scattering of phonons affect the mean free path. Okay. The second thing which affect the mean free path is geometrical scattering. Geometrical scattering of phonons. That means interaction of phonons with the crystal boundary or lattice imperfection or some impurities in the chemical impurities in the crystal. So we know that the mean free path is inversely proportional to temperature. We have discussed how this temperature dependence is coming. At low temperature, so this mean free path become comparable with the width of the crystal. Okay, when temperature decreases, mean free path increases, and at low temperature, the mean free path becomes almost comparable with the width of the crystal, the dimension of the crystal. Okay, so when temperature decreases, the mean free path increases, and it is limited by the dimension of the width of the crystal. This is the geometrical effect on mean free path. Therefore, the thermal conductivity coefficient become function of dimension of the crystal. Therefore, we can write the thermal conductivity coefficient kappa is approximately equal is of the order of CV into, instead of mean free path we can write the diameter of the crystal CVD. Okay, so here at low temperature the mean free path is restricted by the dimension of the crystal or width of the crystal or diameter of the crystal, but at a high temperature the mean free path is restricted by the Ohm-Clap scattering. Therefore, At low temperature, the Umklapp process become ineffective in restricting the mean free path, and the size effect become dominant. Size effect means it is the mean free path is limited by the width of the crystal at low temperature. So this become dominant. Therefore, we can write K equal to CV into D. Here d is the diameter of the specimen, which is a constant. V is the velocity of phonons in the specimen, it is also constant. Here C is the heat capacity per unit volume of the specimen or crystal at a constant volume. So this is only the temperature dependent term in this equation of the thermal conductivity coefficient K, kappa. Okay, so this is at a low temperature. At low temperature, the thermal conductivity is more restricted by this quantity D, and C, the heat capacity at constant volume at low temperature is proportional to C is proportional to T cube at low temperature. That we have studied already. Low temperature. Okay. So when temperature decreases, it decreases as the heat capacity decreases as T cube. So at low temperature and at a high temperature, the thermal conductivity decreases. Okay. So the graph for this thermal conductivity as a function of temperature is like this. This is the temperature in this axis, and here kappa in this axis. The thermal conductivity coefficient kappa has maximum value at a intermediate temperature, and at a low temperature as well as at a high temperature the thermal conductivity decreases, because at high temperature due to Umklapp scattering the mean free path decreases, and at low temperature the mean free path is constant, that is equal to the diameter of the specimen, but the heat capacity decreases at low temperature as T cube. Okay. So this is in very good agreement with the experimental result. So the plot of the experiment is given in the graph in Kittel. Okay, so you can see that.